Good morning, everybody. I have a quick question from one of you guys regarding problem 45 from chapter 23. This person has a question about that problem and how to tackle it. That person understands that we did something similar to it in class, so I'm hoping that this will answer his question, and you guys also, in case you have a question about that problem. So anyway, and I know I mentioned it briefly in the class when we were doing the other problem, that this is going to be tackled in a similar fashion. So problem 45 says that you have a cylinder, a long cylinder, an infinite cylinder as a matter of fact, okay? So it's an infinite cylinder. And the radial direction, instead of calling it R like we normally do, it's called X in this problem, okay? Just because you guys get into the habit of integrating over X so that you get into that situation also, which is your familiar situation. Anyway, the arguments of symmetry in this case will argue that, first of all, the electric field is radial. That means that's the only component of the electric field that's going to survive. Turn it around, left or right, or flip it around. If you take any other direction other than the radial, nothing would keep that symmetry. Number one. Number two, also that the electric field only depends on X, because if you argue otherwise, then it can move up and down the infinite cylinder. It would look the same, but you're saying that it may depend on the value other than X. So if I'm the same location, so in this case, it should only be the same value because nothing changes in the underlying structure other than this value. So those are the 2 points that will come from the argument. There are two key things in here. The radius of the cylinder, I don't know what it was called in this problem, because honestly I don't have it, and the person they said that they sent me the image, I didn't see it, so I briefly looked online and I think I found what the problem looked like. So this is what I remember. So this is the radius R, the maximum radius. So X can be anywhere between 0 all the way to R inside, and outside, of course, X is greater than R, okay? So that's the question. We're trying to find the electric field inside and outside. If we use Gauss's law, that basically states that the flux of the electric field is the same as the charge enclosed divided by epsilon naught. You have to be careful with that epsilon, and sometimes people forget it when you're dealing with Gauss's law, okay? And that gives you a ridiculous number for the tiny number for the electric field. So you need to adjust for it. Anyway, so the point is we're going to do it inside and outside. Before we do that, we need to deal with this flux. Because of the symmetry involved, the flux is going to be radial. Therefore, if I take a Gaussian surface, so this is my Gaussian surface, obviously it depends on X, okay? Its radius is X, doesn't matter whether we're inside or outside. And that Gaussian surface, again, it's a cylinder, but I need to choose a length for it, which is L. Obviously, the contribution of the electric field from the above surface is 0 because of the fact that the electric field and the surface are perpendicular to one another. Therefore, I have a cosine of 90 degrees. The same thing in the bottom also, the flux of the electric field below is 0 too, because I have a 270 degree angle between them. Cosine of 270 is also 0. So the electric field and the area are perpendicular. Therefore, the only side that is going to contribute is the lateral side. The lateral side can be open, and it has a length L and a width, which is the circumference of the circle whose radius is X, so which is 2 pi X. So basically, that's the only contribution, and both of them, the area and the electric field, are radial. Therefore, there is a cosine of 0 degrees involved in here. So the flux on either case is going to be 2 pi X times L. This equals to inside for X less than or equal to R, and for X greater than or equal to R, and I'm going to address the issue exactly what happened when X is equal to R. It's going to be 1 over epsilon naught times the charge enclosed. The charge has a C, of course, and the integral here extends up to X only, where X is less than R, of X cubed divided by nothing. X cubed times the element of volume dV. And in here, that's the integration over dV. But it's a one-dimensional problem, so here is why. If I take an extended version from all the way to X, we're looking where the charge is. So inside, that's the extent with which. Okay, so X is less than R in this case. So I'm going to take a circle whose radius is r, as the radius is x. Again, I have to pay attention. And of depth x plus dx, in other words, the depth of dx. So that's the strip I'm looking at. If I take that and open it up, its length is going to be the circumference of the circle whose radius is x, so it's 2 pi x, and whose height, or width in this case, is actually dx. And this extends in L length. So this is the strip we're looking at in here. This extends deep down in L length, okay? So the element of volume is going to be dV in this case. In either case, is going to be 2 pi xl dV, okay? dx, I'm sorry, dx. It's this area, which is 2 pi x dx times L, okay? So that's the dV in here. And again, the same thing, this expression is going to be c over epsilon naught, but the integral stops at r when we are x greater than or equal to r, because that's the charge enclosed. It goes all the way to r. So now, if we're careful enough and sub the value of dV, so on one side we have 2 pi xl times E, of course, that's the flux, times E. The whole point is to find E, is equal to, for x less than or equal to r, and for x greater than or equal to r, is going to be equal to, again, 2 pi L divided by C epsilon naught times C, divided by epsilon naught. The integral from 0 to x, I have x cubed. Why is it x cubed? It's an x squared. I'm sorry. The value of the rho in this problem, rho is actually cx squared. Rho was given to be cx squared. So I need to be careful in here. I'm kind of anticipating an x cubed. That's why I had the x cubed in there. So it's an x squared in here, okay? So I have an x squared, but I already have an x. And the x is coming from the element of volume. It has an x in it. So everything else comes out, the 2 pi L comes out of the integral. I'm left with an x times x squared. So that's going to be x cubed dx. And the same thing for the other side too, except that the integration is bounded to the other side. So again, it's 2 pi L times c divided by epsilon naught, the integral from 0 to r of the same thing, x cubed dx. Now, the 2 pi L and the 2 pi L and the 2 pi L on both sides cancel. And that's good, because L is actually not the real value. It's just a part of the Gaussian property. So on one side, we have xe is equal to, well, the integral of x cubed is just x to the power 4 over 4. So it's going to be, for x less than or equal to r, it's going to be equal to c divided by epsilon naught divided 4 epsilon naught times x to the power 4. So it's going to be c divided by 4 epsilon naught c over 4 epsilon naught times x to the power 4, okay? And for x greater than or equal to r, it's going to be the same thing, except instead of x, we're going to put the value of r. So it's going to be c divided by 4 epsilon naught times r to the power 4, okay? Identical, except in here I have bounded integral, and in here I have an unbounded integral. Okay, anyway, so now we have to divide by x, and we have found the value of e. So e is equal to, for x less than or equal to r, and for x greater than or equal to r, I have, so we need to match these two values. So the x to the power 4 and the x cancel. So I'll be left with cx cubed over 4 epsilon naught. And in this case, I will be left with c to the power r to the power 4 divided by 4 epsilon naught x. I can't cancel x and the r. Anyway, here it increases as x cubed, and here it drops like 1 over x. What happened when x is equal to r? In either case, it should be the same value. So the first one gives me cr cubed divided by 4 epsilon naught. And the second one gives me cr to the power 4 divided by 4 epsilon naught times r, cancel the r with the r4. And it's equal to the same value as before, cr cubed over 4 epsilon naught. So the point being in here is that this is a continuous function, albeit it doesn't have a derivative when x equals to r. Other than that, this is the value of the electric field. It grows as we go and encounter more and more charges, and these charges are actually increasing as a quadratic function, so they are not increasing linearly. That's why the electric field is increasing more than that, okay? It's increasing as a cubic law. But then, once we reach the boundary of the cylinder, at that point, we have encountered all the charge we can. Therefore, at that point, its effect starts to drop. The further away, the electric field starts to get weaker and weaker, and drops like 1 over x. It doesn't really drop like 1 over distance squared because of the fact that this is a long rod. As I'm moving away further and further, I'm encountering more and more contributions from the faraway edges of the cylinder. So that's why it doesn't really drop like 1 over distance squared. Obviously, this distance should not be of the same size of the cylinder, otherwise this infinite rod approximation will not be true. Anyway, so this is hopefully helpful for problem 45 from the assignment that you guys have. And I know you're not necessarily required to submit this problem, but at least you guys know how to do this problem just in case, to understand it, because it's supposed to be helpful. I know you have other problems to submit from this chapter too, okay? If you still have any questions, please guys reach out. Thank you.